Hi, everyone. My name's Abby, and this is our project 23117 about natural gas recovery from oil refinery. Let's meet the team. So my name's Abby.
My name's Reagan.
My name's Hayden.
And I'm Elena.
And we're all senior chemical engineers.
So this is our poster for our project. The big conclusions are that the natural gas has to re-enter the well at just over 12,000 PSI. All of our electricity will be generated from our fuel gas, and the overall process costs just around $66 million.
So now we're going to get into how we got there. So our process is focusing on an oil well in Alaska, and our objective is to improve the current state of pumping oil, which is reinjection of gas or water after the oil well is already established and pumping. So our process does it before then, while in the creation of the oil well. And so we're focusing on separating the oil and water from this natural gas to reinject, and we used Aspen to simulate the separation. So when oil is extracted from this oil well, there is a pressure loss when you're pumping out. And so in order to reestablish this pressure in it to maintain a good pumping of this oil, we have to reinject natural gas. And we also use some of this natural gas to power all the rest of our equipment. So as I said, our objective is to optimize an oil recovery system, and we're also throwing in some strong safety parameters. And our criteria and our focus is high % recovery of this natural gas and using it to power a turbine.
So let's get into the process summary. So here's our block flow diagram. This is sort of a big picture scope of our process. So it goes from the original 3-phase separator and follows the natural gas into a knockout drum. And the two main uses for this natural gas are the compressor to be re-injected into the well, and also to be used in the combustion gas turbine to power the compressor, as well as showing a heat exchanger that recycles just in case we need it, as well as a cooling water loop associated with that.
So going after Hayden's lovely VFD, this is the process flow diagram. It's a diagram about all of our different unit ops, as well as some important control valves associated with the process. As we can see, our 3-stage compressor is probably the most important equipment on this diagram. We need to re-inject the gas at a high enough pressure to reestablish the pressure in the well. And this stage gets really hot, so we need interstage cooling with that, which is supplied using the utility water seen below.
So here are our piping and instrumentation diagrams. Starting with the 3-phase separator, which is out of scope for our project, but we made a P&ID just in case. And this has level controls as well as pressure controls at the top, which that natural gas stream is the main important part of the unit op. So going into the knockout drum, we have a boot at the bottom of the knockout drum, which allows us to measure the level and have high alarms just in case there's too much liquid being collected at the bottom. And here is our 3-stage compressor. This takes the power from the combustion gas turbine, as well as the natural gas, to then pressurize it just to 12,000 PSI. And this includes also interstage cooling with recycled coolers. Here's the combustion gas turbine. So this takes some of the natural gas and combusts it to create the power for the compressor, as I said before. And here is our recycle heat exchanger, where we have the associated cooling water loop, which includes the air cooler, the expansion tank, and the water pump. And there are pressure and temperature controls, which are associated with those streams. So let's get into the equipment breakdown. So starting out with the knockout drum, the reason why we have this knockout drum is to get rid of the entrained liquids that are still in the natural gas, just to make sure we have as pure of natural gas as possible for our uses.
So we settled on only having one knockout drum by using Aspen, and we used it to simulate the separation of both the 3-phase and any knockout drums. But as we said, we settled on only using one because the vapor fraction coming out of that knockout drum is 0.98, and we ensured that the temperature and pressure is high enough that nothing else will condense out of the vapor.
So for the 3-stage compressor, the reason why we need 3 stages is because we're jumping up pressure from 500 to 12,000 PSI. And when you do that, it gets really hot. So we need interstage coolers. All of the stages of the compressor are about 34,000 horsepower, and we wanted to even these out so it can be the most efficient as possible. So it costs about $28 million. So for the combustion gas turbine, it's rated for about 6,000 kilowatts. And this is basically just what's going to be used to power the compressor. And then for the heat exchangers, we have 3 main heat exchangers. There's two interstage coolers and 1 recycle cooler. And they're all about the same size because they cool the water and the process streams to the same temperatures. So they're all about 90,000 square feet, and they all cost about $2 million. And then for the air cooler, this is what's going to be cooling, the cooling water that cools the process stream. So they're about 5,000 or 5 million square feet. And this is just using air to cool the water, and it costs about $4 million.
Then the water pump is what's moving our utility water to the future unit operations. And our size, it runs at around 400 horsepower and is around $85,000. And the expansion tank is sized to be 20% of additional cooling water in case of any safety reasons, and a 20% overhead for the same reasoning.
So let's get into the cost breakdown. So the big takeaway about the cost is that we're going to be profitable by year 5, which is really big deal because it's going to take us 4 years to build the plant. So we don't even make any profit until the 5th year. And so the cost to build the plant is about $66 million. 60% of that is equipment, 38% is manufacturing, and then 2% is the depreciable wages and benefits. Then as you can see from the cash flow diagram, as the years go on, we just continue to be profitable.
Just some general conclusions. We have reestablished the pressure in the well and reduced the utility costs beyond the scope of this project, as well as produce more oil than if we did not use reinjection. So we're net profitable for many oil companies. Thank you, and bear down.